Now we're going to look at absolute value on a Cartesian graph, an xy plane. So here is the parent function of absolute value. It has two straight lines that meet at a vertex. The parent function has the vertex at the origin, and each of these lines has a specific slope. The line going to the right has a slope of +1. The line going to the left has a slope of -1. The domain of any absolute value function on a Cartesian graph is always going to be -infinity to infinity. It's always going to go from the far left to the far right. And the range is always going to be the lowest value to the highest. The parent function's range is 0 to infinity with 0 included. This graph is not going to have any holes in it, so we won't have any parentheses next to numbers in our range. Now, the graph won't always look exactly like this. So we have different transformations on that graph that will happen. Inside of our absolute value, if it has x minus a number, our graph is going to shift to the right by that amount. So if it says x minus 1, our graph is going to shift to the right 1. If it says x plus a number, it's going to shift to the left by that amount. If we're adding a number outside of the absolute value, so we have the absolute value of x plus a number, that's going to move your graph up. If you're subtracting a number on the outside of your absolute value, that's going to move your graph down. If you have a negative sign in front of your absolute value, where it's attached to it, like it's being multiplied by -1, that's going to reflect your graph over the x-axis, so it's going to look like an upside down V. And then if you have some other number out front, that's going to either compress your function or it's going to stretch it up even higher. By compress, I mean it's going to flatten it out, getting closer and closer to the axis, the x-axis, or it's going to stretch it upward and make it taller and taller and taller, depending on what that value of a is. If a is a fraction between 0 and 1, it's going to compress it, make it flatter. If a is greater than 1, it's going to stretch it up higher. So let's look at some examples. Here we've got y equals the absolute value of x plus 4. This plus 4 is outside of our absolute value, so this is going to be a shift up. So we're going up by 4 units. We don't have anything inside of the absolute value bars, so we're not going to the left or right, and we don't have anything out front, so we're not going to reflect, stretch, or compress. So all that we're doing is from the origin, we're going to go up 4 units. That's where our new vertex is. Then our slopes are not changing. We're still going to have slopes of 1 and -1. So I'm going to go to the right, I have a slope of 1, and to the left, I have a slope of -1. And that is the graph of this absolute value function. For every absolute value function ever, our domain is from -infinity to infinity, or you could see all real numbers. Our range is from low to high. The lowest that this graph gets is at the number 4, and then we have these arrows pointing upward forever, so we're going up towards infinity. So our range is from 4 to infinity. Number 2, we have 2 times the absolute value of x plus 3 minus 2. So this 2 on the outside is telling me I'm going to stretch by 2 units. Stretch by 2. That's what's going to change our slopes. That's like our new slope. The inside tells us left or right. If it's plus on the inside, we're going to go to the left by 3 units. If it was minus on the inside, we would go to the right. And then if it's minus on the outside, we're going down by that number of units. So first I'm going to find my vertex. So from the origin, I'm going to go to the left 3 and down 2. 1, 2, 3, down 2. There is my new vertex. Then this stretch is going to change my slope. So instead of having a slope of 1 and a slope of -1, now I'm going to have a slope of 2 and -2. So my new graph is going to look really tall and skinny. So let's use that new slope and plot some points. So from our vertex, we can go up 2 and to the right 1. We can also go up 2 and to the left 1. Then when we're going to the right, we can keep going up 2 to the right 1, up 2 to the right 1. If we keep going to the left, up 2 to the left 1, up 2 to the left 1 until we run out of room. And there's our graph. As always, the domain is from negative infinity to infinity. The range here, the lowest that this graph gets, is at -2, so we're going to start at -2 with the bracket, and the arrows are pointing upwards, so it's going towards positive infinity. Alright, last one. This negative sign in front of our absolute value says it's going to be a reflection, which means our graph is going to turn upside down. If we're subtracting 2 on the inside, we're going to the right by 2. If we're adding 2 on the outside, we're going up by 2 for our vertex. So from the origin to the right 2, up 2, there's our new vertex. We're reflecting, but there's no number in front of the absolute value bars, so we don't need to change the slope. It'll just be upside down. So we still have slopes of 1 and -1. And here's that graph. Domain, negative infinity to infinity. Now this time for our range, we've got the arrows pointing downward, which means we need to start at negative infinity. So when our graph is upside down, our range is going to start at negative infinity. And then the highest that this graph gets is at 2. So we're going up to 2, and we got the bracket. And that is how we graph these different transformations of absolute value.